M estimators in classical settings. Go ahead.
Yeah, so thank you to the organizers for the invitation. So today I'm going to talk about some sort of classical sort of statistical problems, and sort of the philosophy is to study M estimators and to sort of look at some settings which maybe were missed in the classical work where they have sort of surprising sort of suboptimal behavior. So the first part of the talk, I'll talk about the lasso. The second part, I will talk about maximum likelihood. So the first part is the lasso under anisotropic design. It's based on this preprint, which is joint work with Kang Ma, who's on the faculty in Chicago. So, I'm sure many of us are familiar with the lasso, but just as a reminder and to sort of set notation, so, the lasso is this highly popular tool for sparse linear regression. So throughout the talk, I'll write my matrix of covariates as this capital X. Y is a vector of labels. And what the lasso does is it minimizes this sum of squares plus a multiple of the L1 norm. It was proposed actually by some geologists in the 80s, but maybe most sort of well-known is this paper of Rob Tibshirani. And let me maybe put this in full screen just to, I don't know if this will be what I want, but let's see. So it has some very desirable properties, right? Oh, that's not what I want. Sorry, 1 second. Okay, so it's a convex program. It's amenable to computation. Lots of widely available code in your favorite language, and we sort of know that this L1 norm promotes sparsity, and this is why this was sort of became so popular, particularly in high-dimensional settings. Okay, and so now we get to the sort of statistical theory on the lasso, and I won't try to do an exhaustive sort of literature review here. There's upwards of 30 years of work on this, but people typically look at some type of linear regression model akin to the one I have here. So yi are the labels. It's a linear function plus noise. Theta stars is the underlying parameter, and the sort of work on the lasso sort of requires, at a very high level, two main assumptions. The first is, of course, some sort of sparsity notion in the true parameter. That's why we have the L1 norm there in the first place. And the second is this sort of some type of form of isotropy or near isotropy. So all these conditions, restricted isometry, restricted eigenvalue, restricted strong convexity, compatibility, blah, 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 sort of the list goes on. They all are trying to, in some way, quantify a form of near isotropy of the covariates. And so the starting point of this work is just sort of a very naive question: what if X is anisotropic? So in some sense, X transpose X, this Gram matrix is very far from being a multiple of the identity. Okay, and sort of getting to the punchline, we'll see that the lasso can sort of fail spectacularly. Okay, but so I will retain the sparsity assumption throughout the talk. So let me just sort of say what that means. So there will be two forms of sparsity assumptions. The first one is just assuming that there is a fixed and small number of non-zero entries in the underlying parameter. So that's strong sparsity. And then weak sparsity is you allow for some small tail, right? And the way you quantify that is in terms of these quasi-norms. So for p between 0 and 1, we define this norm just like you would in the convex case. And we have these sort of LP balls, or balls in air quotes. Okay, so this is a sort of weaker form of sparsity assumption. And so I'm actually going to focus on a low-dimensional setting here. So we're going to look at the case when the number of samples is larger than the dimension. And you might say, well, why are we doing this if we're doing the lasso? I mean, so the first point is that this is a talk about lower bounds. So if I give you a lower bound at the low-dimensional case, and in our paper we talk about how that implies something in the high-dimensional case, but it already fails in the low-dimensional case. And secondly, you can also view this as just maximum likelihood estimation, right, over your LP ball. Okay, but the reason we want to sort of work in the low-dimensional case is to come up with sort of a a simple class of design matrices to look at. So we're just going to look at fixed design problems where the fixed design satisfies the following lower spectral condition. So the Gram matrix has an eigenvalue which is bounded away from 0. How far it's from 0 is quantified by this 1 over b parameter. B is positive. So already you see this definition doesn't make sense in the high dimensional case, right? So this is truly here about low dimensions. Okay, yeah.
How small is d comparing to n?
So we can take d all the way to n for the results I'm going to talk about. And then in the paper, we also talk about a random design setting where we discuss what happens with in the high dimensional case. So here, of course, you could rephrase this as a constraint on the lower singular value of your design matrix. Intuitively, what you would expect, right, is the larger this b gets, the weaker my lower bound, the less information I have in my problem, and the harder the thing will get. And indeed, we will see that that's the case. And if you are sort of a statistician trained in the 70s, you could also view b as a sort of upper bound on the Fisher information for this problem. And the original motivation for this particular setup was from a sort of transfer learning problem, which I might maybe discuss at the end if there's time. But there's a good reason for why we formulated it this way. So let me start with sort of a basic result, which is sort of the optimal rate of estimation for this problem. So I'm going to assume for the purposes of the slides here that the noise level is sort of order 1. I'm also going to take the constraint radius to be order 1. So we have basically 3 parameters: the dimension, that's d, the number of samples, n, and p, which is the order of the norm constraint. Okay, and so here's what we have. So assuming that d is less than n, for moderate sample sizes, what we can say is that the minimax rate for this problem scales as follows. So maybe I'll just say a word about what's on the left-hand side of this equation. So what we're looking at is estimators that work uniformly over this class, right? So they work uniformly over the class of design matrices that are b-bounded, and they work for any LP norm constraint, right? That's the idea. And so so we're looking at the best worst case error, and it scales as follows. So you can see the expression on the right-hand side. So just to maybe a couple of comments, right? So as p goes towards 0, the rate gets faster. So it's roughly of the order b over n. At p equals to 0, it's like square root b over n for p equals to 1. And what does moderate sample size here mean? So moderate sample size means the following. And so there's a very good reason for this. So if you are outside of this sample size regime, then this problem is totally uninteresting, right? So if n is smaller than b times 1 plus log d, then you can't do anything in the minimax sense. So you can't do anything better than outputting 0. Okay? And on the other hand, if n is larger than b times d to the 2 over p, nothing can really beat ordinary least squares. So sort of the interesting regime is precisely when you're in the middle here. And so I will focus on that for the lower bounds against the lasso, because this is sort of where you would care about using some type of shrinkage estimate. Okay, and so just a word on how you prove something like this. So both the upper and the lower bounds are based on reductions to the Gaussian sequence model. And then, and I'll talk about this in the second part of the talk, actually, the results for the Gaussian sequence model were sort of classical. So these were known from the 90s. Okay. Any questions about the rate? Great. So now we'll move to the suboptimality of the lasso. So it turns out you can make the lasso fail already with just 2 singular values. So as soon as you have 2 singular values, the lasso is hosed. So what we're going to look at is design matrices that have the following Gram matrix. So the Gram matrix is 1 over b, and half of the coordinates are alpha over b. The other half are just 1 over b. So this certainly satisfies the b-bounded constraint as long as alpha is larger than 1. And what we can show is the following. So for some choices of alpha, the lasso is rate suboptimal. So specifically, we have the following. So if I look at any fixed alpha, I look worst case over the parameter space for any p, what we have is the following lower bound against the performance of the lasso. And so just to look at the left-hand side here, what it's I'm lower bounding the error of the best choice of regularization, right? So that's why there's an infimum on the on the inside. So basically what it's saying is that the entire path is suboptimal, no matter what you do. So you cannot fix this by doing constrained, regularized, cross-validated, whatever you want to do. The lasso path is hosed for this problem. Okay, and sort of just to see why this lower bound is sort of precluding the optimality of the lasso, just the issue is if alpha is large, right? So for a certain range of alpha, the middle term will dominate, and we'll see that it's rate suboptimal. So let me just give an example of that calculation for you. So let's just look at a particular scaling of the parameters b, d, and alpha. So I'll take d to be of the order n, b to be of the order root n, and alpha to be of the order root n. So I'm looking at a design matrix that has a condition number of square root n. Okay, then if I instantiate the previous result in this setting, what it says is that the worst case performance of the lasso is order 1, okay, which is as bad as it could be. Okay, in comparison, the minimax rate here is sort of fast, right? So it's like 1 over n to the 1/4 up to log factors if p is equal to 0. Okay, so the lasso in this case is off by quite a bit. So just to sort of see what happens, so let's look at the lasso with its sort of optimal choice of regularization. So this is the regularization you'd pick if I told you theta star. So this is, of course you couldn't actually implement this in practice, but we're trying to be favorable to the lasso, right? So this is the best choice of regularization I could have. And then I'll compare against a very simple estimate, which I'm calling soft thresholded ordinary least squares. This is just a 2-stage procedure. I do ordinary least squares, and then I do a shrinkage to it. So that shrinkage is just soft thresholding. Okay, so it's just 2 stages, and that one is actually minimax rate optimal. And so what you see is the following. So I'm doing the same sample size sort of scaling that I had on the previous page. So it's the same, the same setup here. And what I'm showing you is the performance of the lasso versus, a minimax optimal estimator. And indeed, it's as sort of the theorem would predict.
Sorry.
Yeah. So it's just, so what I do is I first run ordinary least squares. Then what I do is I essentially do like a weighted projection. It's just the proximal operator, right, for L1. So it's just soft thresholding. That's all. And lambda depends on the configuration. So it depends on the amount of soft thresholding depends on the configuration. So it depends on the noise level, the dimension, and things like this.
Estimate those things online?
So you can do it. In this case, we're in the low dimensional case. You can estimate it consistently. Yeah. So this simulation is just using knowledge of it. But yeah, you could also in this case you can actually also do that from the samples. Yeah. Okay, so that was sort of the first sad story. So lasso fails with sort of even just 2 singular values. The second part, I'm going to talk about mean estimation over LP balls, and this one is a more recent work and joint work with some colleagues at Berkeley, and so I'm very happy for any sort of comments and suggestions that you guys might have. Okay, so what is the setting here? So the only problem that's simpler than linear regression is mean estimation. So we're going to do mean estimation now. So we're given IID observations. So I give you n Gaussian observations, signal plus noise. And again, I'm going to assume that it's LP norm is controlled. Okay, and the goal is to estimate theta star. So very, very classical problem. The goal is to achieve the optimal mean squared error, right? So I assume that my parameter lies in a LP ball of radius r. There's noise level sigma, dimension d, norm index p, and samples. So right now there's 5 parameters. There's r, sigma, d, p, and n. Okay, we're going to get rid of a few in a minute. And the good news here is that the minimax rate is not the interesting part of the story. This was well known, for now 25 or maybe 20-ish years. So the question is, how does the maximum likelihood estimator perform? Okay, you might think, well, surely that's known. Yeah, it's quite surprisingly, it actually was not prior to this work, and as we'll see, it has some kind of funky behavior. So this is it's just projection, really, right? I'm taking the average of the L2 difference between my observations and theta, and finding the one that minimizes that over the constraint set. So that's the maximum likelihood estimator in this setting. Sort of, very well known or easy to see that I can assume without loss of generality that I have just one sample, it just rescales the noise level. I can also take the radius to be order 1 and get all the results for unit radius and just rescale afterwards. So just to simplify, I'm going to remove the parameters n and r. We're going to look at everything just in terms of sigma, p, and d. So these are the only interesting parameters now. The norm constraint is 1, and I have one sample. Okay, we can always translate backwards. Okay, so there's an important paper of Donahoe and Johnstone from the 90s. This is the work that I was saying that sort of established the min-max rates, which maybe some of you are familiar with. If not, I'll give you sort of the main takeaway now. So what they did in this work was they determined the asymptotic min-max MSE for all p, and what they were interested in was the performance of linear estimators versus nonlinear estimators. So as a consequence of their results, what you can see is the min-max rate, so we'll start with that. So when p is larger than 2, the min-max rate for this problem has the following behavior. It's the minimum of 2 terms, and this has a very simple sort of description, right? Basically, in this case, the LP constraint is really not that helpful. Either you're in a setting where the noise level is very high and you cannot beat just outputting 0, okay? And that's d to the 1 minus 2 over p. That's just the Euclidean radius of the LP ball squared. Okay. The other term is if the noise level is small. If the noise level is small, then just the observation itself is already rate optimal, and that would get me sigma squared d. So these are the 2 terms, and that turns out to be the whole story for p larger than 2. So p less than 2 is where things get interesting. So then things get more interesting. So again, there's these 2 regimes. If the noise level is very large, specifically the noise level is larger than 1 over log d, roughly, then you cannot do better than outputting 0. And 1 is the Euclidean radius of the LP ball. Or the noise level could be very small. Sigma squared d is optimal. And because we just outputting the observation itself is already rate optimal. And then there's this intermediate regime. That's when the noise level is between these 2 levels, 1 over d to the 2 over p, and 1 over 1 plus log d. There, you can do something. So there are shrinkage estimators that will do better than these 2 rates. And so we'll talk about that in just a minute. But this was the sort of main observation or one of the main observations of Donahoe and Johnstone. So yeah, like I said, there's this moderate noise regime where some non-trivial procedures are required to sort of attain rate optimality. Okay, and so this will be, again, just like I mentioned in the first part of the talk, I'm going to mainly focus on this middle regime because the other 2 are, sort of trivial, right? Okay. So the other kind of interesting point from this Donahoe-Johnstone paper was what they referred to as, or what Johnstone referred to later as sort of a nonlinearity phenomenon, which is when linear estimates can work versus when they cannot work. So one of the main insights of this paper was that the linear minimax risk, so that means the optimal error among linear procedures which are linear in the data, versus nonlinear estimators could be arbitrarily large in sort of the high dimensional case. So specifically what they said was the following. So in a setting where the norm index p is fixed, sigma is allowed to depend, the noise level sigma is allowed to depend on the dimension, and d is taken to infinity. They looked at this competitive ratio between the best performance of linear estimates to the general minimax risk. Okay, and it turns out that this is actually infinite. It blows up in high dimensions whenever the noise level is in that moderate regime. Okay, so that was one of the main results in this paper. And so sort of like a slogan or main sort of takeaway here is that if the LP constraint is useful, right, is meaningful, then linear estimates are going to be arbitrarily bad when the dimension is large. Okay, that's the main takeaway. And what we're going to see here, just sort of momentarily, is that something very similar happens to the maximum likelihood estimator, despite the fact that it too is nonlinear. Okay, so before I get to our results, I just want to take maybe a few minutes to mention the related work here, because some of it is quite recent and I think also very relevant. So, sort of in the sort of math stat literature, there's tons of work on the suboptimality of the maximum likelihood estimator or the least squares estimate, depending on who you are. And it at least goes back to Bourget in the 80s. Bourget and Massart had a number of papers pointing out the suboptimality of the MLE in various settings. Lucien Lecomte was also very famous for advising against the maximum likelihood estimator. And then sort of more recently, work from Saurav Chatterjee, Aditya Guntaboyina, Gil Kerr, Sasha Rocklin in various forms of suboptimality of the MLE. And so another piece that's related here, and I'll explain why this is important in a minute, is sort of sharp estimates of the local Gaussian width of the LP ball. Maybe I'll comment about that in just a minute. But getting back to the suboptimality of the MLE, so there was this paper of Saurav Chatterjee in the Annals in 2014, and one of his main results was that the mean squared error of the maximum likelihood estimator at a point in the parameter space was related to a maximizer of this function of epsilon. So what I do is I look at the local Gaussian width, at radius epsilon around my parameter theta, and I look at the difference between this expected Gaussian width and epsilon squared over 2 sigma. Okay, and I try to find the epsilon that maximizes this, and essentially it turns out that this controls the squared error. Okay, so that's one of the main results in this paper of Chatterjee. So given that, you might think, well, if I want to show that MLE is suboptimal, the natural thing to do is just compute this thing for points in my parameter space and see if it matches the minimax rate or not. Okay, now unfortunately, we don't have really the tools to do that. So why don't we have the tools to do that? Well, because it sort of requires you not to estimate the maximum likelihood, the local Gaussian width up to multiplicative constants, but you need to estimate the local Gaussian width very precisely in order to use Chatterjee's results. So this result, in fact, Chatterjee mentions this in his own paper, is that to derive explicit risk estimates using this, can be quite challenging. So yeah, it's quite difficult to effectively control this guy for the LP ball, but it is certainly related. And unsurprisingly, Gaussian widths appear all over our paper. So paper from more recently by Gil Kerr and some of his co-authors, he showed that for essentially symmetric convex body, so if my parameter space is essentially symmetric convex body, as it would be in the case of this LP mean estimation problem for p larger than or equal to 1, the MLE is rate optimal near the origin. So specifically what he shows is that the variance of the maximum likelihood estimator near the origin is minimax rate optimal. Well, actually, the variance is always minimax rate optimal, that is the error at the origin. And so what this means for us and for our problem is that if the MLE is going to be suboptimal, then it must be near the boundary. Okay. Unfortunately, the boundary is also where it's very difficult to effectively estimate the Gaussian width, and so our lower bounds will not actually come directly from the Gaussian width. Yeah. Yeah. So this is Gil, by the way. He's one of the co-authors on this paper, not on this paper, but on that paper that I'm referring to here. Yeah. So the reason why the idea in this paper is that if I give you essentially symmetric convex body, then at 0, for example, there's 0 bias, and this is just because the noise, right, is symmetric, and so the bias is 0, and so what he showed was that the variance is minimax rate optimal throughout the parameter space. So hence, at the origin, the MLE is always rate optimal for a convex constraint set. Was there another question, or okay, great. And then finally, a very recent paper from a group at CMU. They also were interested in trying to characterize optimality versus suboptimality of the MLE in various settings, and they came up with a condition. Unfortunately, that condition, it would be wonderful if one could come up with a direct proof using that condition for the LP case. I suspect that will be really, quite challenging. So, but I wanted to mention that, that certainly is related. Okay, so getting to our result. So here's what we show about the MLE. So the MLE has this kind of funky, transition. So there's two cases when the MLE is optimal for all noise levels. So if p is larger than or equal to 2, the MLE is optimal for all noise levels. If p is between 0 and 1 plus 1 over log d, then the MLE is optimal for all noise levels. What's weird is that if the norm index is between 1 plus 1 over log d and 2, then it turns out that the MLE is suboptimal for essentially all noise levels. So there's this bizarre sort of dichotomy. Okay, so to sort of contrast it to Donahoe and Johnstone, what they showed was that below 2, right, below p equals to 2, linear estimates are minimax rate suboptimal. So what we're saying is that so the MLE is also minimax rate suboptimal all the way down to 1 plus 1 over log d. Okay, and then it becomes optimal again, which is, yeah, a bit odd, but this is what happens. So for p larger than or equal to 2, this is essentially immediate. So why is it essentially immediate? Well, because the MLE is just a projection onto the parameter space. So it can never have performance which is worse than the radius squared or the performance of outputting the observation, which was exactly the minimax rate. So for p larger than 2, it's clear that the MLE is rate optimal. So this is not the interesting part. For p equals to 1, it follows from sort of a standard localization argument and this local Gaussian width bounds that I was referring to earlier. This is from work of either Pierre Belec, or if you want to look at a paper of Gordon from 2009, it would also imply this result. Then from 1 to 1 plus 1 over log d, one can derive the result from p equals to 1. So the Banach-Mazur distance between the LP ball for p between 1 plus 1 over log d and p equals to 1 is order 1. So the rate, from that you can easily see that the rate will be, will be minimax optimal again for the MLE. So the interesting thing is what's going on below 1 and to the right of 1 plus 1 over log d. So to the right of 1 plus 1 over log d, then it turns out that the MLE is arbitrarily suboptimal. So in the same way that Donahoe and Johnstone showed for linear estimates. So what you can show is the following. If I have a noise level that's in this intermediate regime, then the MLE has competitive ratio, which blows up as the dimension goes to infinity. Okay, so very much an analogy to Donahoe and Johnstone. And then finally, in the non-convex case, this is where the MLE becomes optimal again for all noise levels. And this is based on developing basically the right local Gaussian width bounds. Yeah, so I'm going to show that here. Oh, for p between 0 and 1. So for p equals to 0, you can, right? Because it's best subset selection, but I have no covariates. So I just take my observation and I just pick the top S coordinates. That's the MLE for p equals to 0. For between 0 and 1, the answer is that you can compute it with probability 1. So yes, yeah. Okay. So just a brief word on the non-convex case. So this is where the MLE is order optimal. So how do we establish that? So the MLE is projection in this case, where remember we have one sample. From that, you immediately get that the error of the MLE, or the error can be bounded as follows, right? I can control the distance between the projection and the true parameter in terms of this this inner product. And then a standard sort of localization argument shows you that the error can then be controlled in terms of a sum of two things. The first is some epsilon squared, and the second term is a local Gaussian width squared. And epsilon here is a free parameter. You get to pick it. Okay. So because the noise is Gaussian, if I take expectations on both sides, what things will boil down to is basically a local Gaussian width of the constraint set that I have there. Okay, which is a local version of the Gaussian width of the LP ball. Okay, so when p was larger than 1, Gordon and Litvak, Mendelssohn, Pajor, they tightly characterized the local Gaussian width. Their arguments used sort of convex polarity, and they were able to obtain basically sharp characterizations of the support function of the local of the local body. That doesn't work when p is less than 1, and so we have to do something different. And just as an aside, the hard sparse case, p equals to 0, no localization is necessary. So for p between 0 and 1, the key observation is that you can take this set of this local set of sparse vectors, and it can be related to a set of hard sparse vectors which have up to constants the same Gaussian width. So what we show in the paper is that if I take this set C d p epsilon, so this is a set of this is the local set of LP sparse vectors. It can be written. It can be related to a set of hard sparse vectors who have essentially the same Gaussian width. Okay, and it's not a very hard argument. It's just based on a form of shelling or peeling. Okay, so you just take your vector in LP and you split it up into its order statistics, and you approximate those with sparse vectors. So this it's about a page computation. Okay, and then if you take this bound that you get from this, so it's trivial to compute the local width of sparse vectors. So if you take this bound and you plug it into this thing here, and you optimize an epsilon, you'll get the optimal rates. So that's the argument for p less than 1. So now just to illustrate for you how the suboptimality result looks like, I'm showing you sort of the two behaviors that occur here. So as I mentioned, the competitive ratio blows up as the dimension gets large in the suboptimal regime. That's when p is between 1 plus 1 over log d and 2. And it turns out there's actually a second phase transition in the noise level. So there's a regime where, that's the one depicted on the left, where in the worst case, the error of the MLE is order 1. So it's actually non-vanishing as the dimension goes to infinity. So it's basically completely useless. And then there's another regime where the MLE has, sort of gets a rate which is going to 0 with dimension, but it's doing that at a slower than optimal rate, right? That's the right-hand side. So the error is still vanishing, but it's just vanishing at a slow rate. Okay. And in the paper we make precise what those cutoffs are. And just so what's being plotted here are three things: the performance of the MLE on an instance, the minimax rate that's the black line, and then in red I'm showing you the performance of this estimator, which I'm calling ST. That's this soft thresholding estimator that was mentioned before. So I just solved this problem, the one that's on the slide with the correct choice of a regularization. Okay. And so sort of the noise level that sort of dictates whether or not I'm in the vanishing case or the non-vanishing case. So if I'm if I'm between 1 over d to the 2 over p and 1 over d to the 2 minus 2 over p, then this is the vanishing regime. The right of that is the non-vanishing regime. Okay, so maybe just a few words on the proof outline for the lower bound, and then I'll wrap up. So the maximum likelihood estimator for the way we establish the lower bounds is not through the local Gaussian width. As I mentioned, if you want to do that, it's I will say good luck. We tried for a while; it was very difficult. So instead, what we are doing is something different. So we can characterize the MLE in this case using convex duality. Remember that p is between 1 plus 1 over log d and 2. So we have duality at our disposal here. And so what we can show is that the maximum likelihood estimator involves solving a fixed point equation, and that's the fixed point equation that I have on the screen. You solve that in the parameter c. So t is fixed, lambda is fixed. I solve it in c. So I'll define c lambda of t to be the solution, which is unique to the above equation. Okay. So it's clearly some form of shrinkage, right? Because if I have, in this case, p larger than 1, so I have to take c to be smaller than t in order to solve this equation. Okay, and then what we show is that the maximum, this is, again, maybe about a page calculation to show through using convex duality that the maximum likelihood estimator sets lambda to lambda star, meaning it solves this equation for lambda equals lambda star, where lambda star is the following. I compute this fixed point equation in lambda, and I find the first time that this thing hits my LP constraint. Okay, so that's the data-dependent notion of shrinkage that the MLE employs. Okay, and so what we show is the maximum likelihood estimator can be written explicitly in terms of the shrinkage map. So the ith coordinate of the MLE is nothing other than the sine of the ith coordinate times the shrinkage with the, the optimal shrinkage value lambda star. Okay, so everything boils down to controlling this lambda star. The idea will be to show that the MLE is suboptimal. What we need to say is that it shrinks too much. If it shrinks too much, then that means that if we show lambda star is large, then what we will be able to show is that the error will be that the MLE incurs is large. So what we do is the following. We consider k-sparse signals that lie on the boundary of the LP ball. Yeah?
The lambda star is the same for all entries?
Yeah, but remember, they're tied by this equation, right?
Yeah, but it's all the same for all entries.
Yes, that's right, yeah. It's the same lambda star for all entries, that's right. So what we do is we look at parameters ground truth, which are on the boundary of the LP ball. Like I was mentioning, from the prior work, we know that the hard instances are somewhere near the boundary, if they exist. So we look at a problem of the following form. I have k non-zero entries, and I pick and I set them all to be 1 over k to the 1 over p, so that the vector has unit LP norm. Okay. It's easy to see that if the noise level is larger than 1 over d to the 1 over p, then typically, for typical realizations of the noise, the vector y will have LP norm which is larger than 1. So in other words, you have to shrink, meaning lambda star will be positive in this case. Okay, the next observation is that to fit the noise-only entries, that's the d minus k entries which have no signal, the MLE must set lambda star quite large. And that comes from massaging that sort of Lagrange duality thing that we had before. And then the point is that if I can show that that lambda star is sufficiently large, then it will force the MLE to shrink in the coordinates for which I had signal, right? And that will lead to the the rate suboptimality. And what is k? Well, k is this sort of complicated looking formula. And if you look at this closely, it becomes 1 essentially right at that transition where it went from vanishing to non-vanishing error. So yeah, and just to show the sort of illustration of what's going on, so you have theta star, you have this noise which is kicking you outside of the LP ball. Because of the lambda being very large, you're being shrunk to some point which is very far from the ground truth. And that's essentially what the proof is showing. Okay, so just to, I guess that's it. So thank you for your attention, and happy to take any questions.
Are there questions? Okay.
Thanks for the nice talk. For the first result on the suboptimality of the lasso, you kind of presented this fixed design hard instance with, right. I think, there's kind of a spike in the first d over 2.
Yeah.
I was curious if you think there's a natural random design model where you think that could be witnessed.
Yeah. So we really didn't want to do this on our first version of the paper because we knew from simulations that something very similar held in random design. It's just a lot more painful. So the answer is yes, and because we've submitted the paper and the reviewers asked the same question, we are in the process of writing down the technical details. But yes, you can do the same thing with Gaussian random design with a covariance matrix, which has the same spectral structure that was done here, and it's essentially you can show the same type of result. It's just the tools are different. Now we have to use Gaussian comparison, and it's a lot more painful. But there is an analogous statement in random design.
Yeah. Just as a follow-up to that, would you need D to be sublinear in N for that? Would you need to be in that regime, or can you get?
Oh, so right, yeah. So you can no. So no, we do not. So you will get a lower bound in the high dimensional case as well. However, so if you look at the lower bound from before, I don't know if I see if I can actually get to it. So there is this term BD over N. This is the error you would get if I take lambda all the way to 0. In the high dimensional case, that's the wrong. If I take lambda to 0, I get the L1 minimum norm interpolant, right? So what you end up getting terms which look different, but they have the same qualitative behavior. There's a term which is basically the lambda small regime, the lambda moderate regime, and the lambda large regime. So it's just that here you'll get something different. It'll be like b over. It'll be like 1 over log dB over n or something like this, right? So it'll be something different, but it will just be the right, lambda near 0 term. So. Yeah.
So thank you for the talk.
Yeah.
I had two quick questions.
Yeah.
One regarding the first part. I was wondering if you, instead of a lasso, you put an elastic net penalty.
Yeah.
Shouldn't that take care of the issues you have?
No. So the reason is that, remember, this, so if in these three terms, the one we want is this guy, not this one. So BD over N is bad for us, right? We don't want a parametric rate. We want something which is better than the parametric rate, because we're in a case where D is large as compared to N, right? So elastic net's not going to help you here. I don't know if that answers your question, but
yes.
Yeah.
And the second question is this. In the second case, the normal means estimation, if we cast it as a decision theory problem in which we have to pick which coefficients are 0 and which are not 0, I was wondering, can you like characterize your results in this from this point of view? Because maybe overshrinkage is fine as long as you don't mess up the the identification of the parameters which are not 0, because usually that's why you do these normal means problems.
Yeah. So. In terms of recovering the support, if that's what you're asking about, support recovery, that so I guess you have in mind the hard sparse case. Well, in the hard sparse case, the MLE is already order optimal, right? So I think maybe that's not the most interesting regime for getting lower bounds. But what I will say so this is not exactly what you're asking, but for P between 1 and 2. Interestingly, if I use this estimate to estimate the norm of the parameter rather than estimating the parameter itself in the L2 norm, then there's a different behavior. So there's a larger regime for which the MLE is optimal if I care about estimating only its norm. So what I'm trying to say is that there are other statistical problems which would have a different base transition than the one I showed today. But I just think the hard sparse case is not one where you'll get statistical hardness from the MLE. So yeah, I'm not sure if I completely answered your question.
Yeah, thank you.
Yeah.
Is there
Yeah, there's one down here. But you can just talk loudly, I guess.
Oh, just wait a second,
okay.
because there are people online.
Thanks again for the great talk. What is the worst P between 1 to 2? Like if you take the competitive ratio between minimax rate and the risk of least squares. The P.
I can get back to you on that in like 10 minutes. I need to look at the paper again. I don't remember.
Oh, you don't have it in the back of your head.
I don't remember the rates. Yeah, it's like I don't remember off the top of my head. But so in here I just talked about the competitive ratio when it's infinite or not. In the paper we characterize the rate. So you can answer that question by looking at our results. I don't remember off the top of my head. Yeah.
All right, I think we'll keep the next questions for the coffee break. Thank you a lot.
Thanks.